Welcome to the channel where all you gotta do is decide whether to use Vanos or not. So, imagine there's a lot of people out there, hundreds even, tens maybe, that are wondering why I decided to put an S85 V10 into a Mustang when the obvious choice would be Coyote or Windsor or 289 or maybe even an FE. I did have an S code 67 Fastback in high school. But I kind of wanted to make this car a little bit more unique. Everybody puts Coyotes and everything, Broncos, LTDs, whatever. Pickup trucks. Not a bad motor. Has its limitations, of course, like all motors, but I decided to use something a little bit more exotic in the V10. So, fully knowing that the S85 is not the most reliable platform on the planet. It has a multitude of issues, some of which are known, some of which are, somewhat known. But I'll go over a couple of them here and explain my logic. So, the main problem S85s have is the rod bearings, which it's a real problem that the rod bearings are a wear item, but it was caused by a couple of issues. So the decision to use a Alumisil block required additive package in the oil that was not the best. Let's just put it that way. Not the best for bearing longevity. ZDDP is a common additive in motor oils to build up a tribofilm on the metal parts. And those tribofilms are used in a regime where there isn't enough oil film, like low speeds or cold start or some oil starvation or some, things happen. So the fact that the ZDP does not work as a tribofilm on the sleeves, they used a different additive pack. So that is not the sole contributor. The rod bearings are, I wouldn't say small, they're a large diameter, but they're pretty narrow. But the oil is definitely a contributor. It's a 60 weight oil, and clearances are maybe a little bit small. There's a lot of contributing factors, but the fact that there's no tribofilm in there, or there's no ZDDP to protect the journals, on this particular build, I am planning on going with forged connecting rods and forged pistons and sleeves to remedy that problem and some other, right? Sleeves solve a lot of issues for what motor oil you can run and the rod bearing issue and sleeve issue, right? Roughing. Some of the other problems that this motor has are the actuators for the throttle. So those have plastic gears in those, and those fail fairly often, and they're quite expensive because they fail fairly often. And you can't just put a used one on because those will fail too. So that's a problem. Another problem is the Vanos pump, which they fail, and when they fail, your dashboard lights up like a Christmas tree, and probably shards of metal are going through your oil system. By the time that Vanos warning light comes on, there's probably a bigger problem, which potentially could also lead to a failure of your rod bearings. My general impression of variable cam timing is it's not really designed for increasing horsepower. In some instances, that can happen if it's a separate cam, like the 2ZZ or a VTEC Honda. That has basically an emissions, drivability, fuel economy cam, and then a high power cam, which during emissions doesn't ever use that. But some of the other systems just phase the cams. So your cam lift and duration are fixed by the cam shape, cam profile. And all you can do is rotate those relative to the engine, so you can phase them. So you can change your intake center line, you can take your exhaust center line, you can change both, and you can do it while you're driving. So that's, that's a benefit. You don't need EGR valves and, air pumps and stuff like that. So you can save the money that it costs to put that into the motor. You can get back with not putting other stuff in the motor. So I understand why the OEMs do it. You get some power gains, and you get some emissions and fuel economy gains as well. So it's kind of a win-win, except for cost money and it's a reliability concern, yada, yada, yada. There's always a downside. So just to prove that to myself, I decided to do a simulation. So this is a program that I bought a long time ago. I forget what year, but early 2000s probably, something like that. But it works pretty good, and it's not based on a lookup table. It actually does physics when you're running it. So maybe I'll put a little video in here. It basically iterates until it gets the volumetric efficiency within a certain threshold of tolerance, and then it goes to the next point and guesses, and then runs a simulation. It's kind of like an FEA program for computational fluid dynamics, right? It guesses, and then it sees how close it is, and then it goes up, went the wrong way, and keeps changing until it gets there. Not trying to teach how algorithms work, but that's basically what it does. So this here is a graph. I put in all the information: cam, lift and duration, cylinder head flow, intake and exhaust flow, intake, manifold flow, throttle body flow, all the information, the bore and stroke, obviously, number of cylinders, put all that stuff in there. And this is the simulation that I got out of it. So this was not contrived in any way. It was just, I put in the numbers. This is what it farted out. Now, with one exception, I couldn't put the valve intake center line, or the cam intake center line and exhaust center line, because it's variable. So I picked kind of a lobe, I think it's 109 lobe separation angle, which I don't like to utilize that term because it doesn't mean anything really. But I put it so the intake center line is 109 and the exhaust center line is 109. So that gives you. So anyway, this is the curve that I got. So it makes just over 500 horsepower. I think it's 510 or something like that. I'd have to go back and look at it, but it doesn't really matter. And 440 newton meters torque, which is about what this transmission is good for. So that's what the curve looks like. Normally aspirated on gasoline with this camshaft with 109 degree separation, intake and exhaust center line, essentially. So then what I did was I ran basically 3 different intake center lines and 3 different exhaust center lines. So I started it at 105 and I made it step twice. So it goes 105, 113, 121, and it does that on the intake and the exhaust. So I have 3 positions for the intake center line and 3 positions for the exhaust center line. So that's 9 permutations, and these are all the permutations here. So you can see the intake center line is 113, exhaust center line is 105, and down on the list there, right? So that's what this is, and this happens to be horsepower. but you can plot torque or horsepower. And this is the difference it makes. Like if you wanted to just put this cam somewhere, anywhere, you could make 400 or 505 horsepower, whatever this is, or you could put it, on this one, which is probably some crazy. Yeah, it's 105 intake and 121 exhaust. And you can see that there's gains, and typically when you gain here, you lose down here. So this is the biggest spread. And this is normally aspirated still, right? This isn't, we don't have turbos yet. And it's a big difference, right? Like if you look at the peak, this is, we'll call that 500. This is, that's 510, right? There's 80 in between there. So yeah, that's like 520. And this one is for 60. So that's 60 horsepower difference between the peaks here and here. So that's quite a lot. And over here it's 200 horsepower. Well, this one's like call that 270 and 400, so 130 horsepower. So quite a bit over here. Now you'd have to have rocks in your heads to, lock the cam down in this position. You want to pick something that's kind of in the middle, right? So maybe this purple one, or that happens to be 113. So anyway, this is just to get an idea of what the BMW engineers were looking at, right? They're going to pick this green line when it's at high RPM, and they're going to pick this cyan line when it's at low RPM, right? And they can change both of them independently. So this is 9 permutations, but it's pretty coarse, right? It's 8-degree steps. So, and this is if you look at the chain, this is number 2 chain, number 3 chain, number 1 chain. It puts them in order of average torque. You can also put them in, peak torque or average horsepower, peak horsepower, whatever you want. Well, whatever you want within those 4. So it just averages, in this case, it averages the torque across this whole range, which is 1,000 RPM to 8,600 RPM. So when you go to twin turbos, things change a bit, right? So I didn't intentionally change anything, but this is a different file. This is the twin turbo file, and this is just S85 file. So there's a few other changes, right? This has obviously twin turbos. It has a different exhaust system on it, so that's changed a little bit. It has a different compression ratio. It has E85 for fuel. So you can't really compare these directly, but I believe this is 12 pounds of boost peak. It's not everywhere. I think up here it's like 11, 10.8 or 11 or something like that, but peak is 12. So, and what I did was I put in even more. I did more runs. I think I did 6 different intake center lines and 6 different exhaust center lines. So there's 36 permutations. But unfortunately, the limitation of this computer program is it will only graph the top 5 and only give you data for the top 5. If you look at these are the top 10. So when you get down to here, 109, 121, you can see it's 109, 121 all the way from there to there. Like the top 10 are the only ones you can see. So that's a bit of a limitation, but I mean, you could do it and get the 10 and get the 10 and get the 10 and get the 6 and plot all of them. But so this is giving you the top ones, it's not giving you the terriblest ones, and you're not going to pick that anyway. So as you can see, the difference, I mean, this is 200 horsepower between here and here, but as you can see, the difference here is only, what's that, 30 horsepower? Maybe, from peak torque to peak torque, maybe 30 horsepower. So just as I suspected, once you put boost to the motor, the variable cam timing doesn't help you that much. And this pump and extra weight and all the giblets that are associated with it and the failure mechanism, it's like, and tuning, right? Lots of time tuning. I'm not sure this is worth it. And you'll notice a lot of racer people, even on Coyotes and stuff, LSs, they just deactivate this variable cam timing stuff. They just like block it out. And this is why, right? It makes a huge difference. NA power is super hard. Like those super stock guys spend, lots of stacks of money to get 2, 3, 5, 10 horsepower, right? Whereas turbo guys, just turn the boost up a little bit. Like it's almost cheating, but I'm not running in any class, right? So I just want the best driving car I can get and the most reliable. So anyway, this is what I was thinking was not going to help me, but I wanted to prove it to myself. So, and this is the first 10 of that run. You'll see it's number 19's run, number 8th run, number 14, whatever. So it doesn't have 1 through 36 on there. And you can segregate this by how much idle vacuum you have, and again, average horsepower and average torque and peak horsepower and peak torque. And then this is segregating. It just throws the one away that doesn't have at least 15 inches of vacuum at idle. So you get a different set. So I just thought I'd show you how this program works a little bit. This is average torque, peak horsepower. So as you can see, we're in the 1,000 horsepower, 1,017, 1,015. It doesn't change a lot. 1,006, one at the bottom. So the difference between the top 10 with this vacuum is only 10 horsepower. Right? It's not a lot, and that pump probably takes close to that. It's a 1,500 psi pump, so they don't run for free. So in order to kind of understand, this was kind of a condensed version, kind of similar to what I did for the normally aspirated stuff. So it only has, it's 3x3 again. So, and obviously this is torque, right? That's right there. So the torque, there's quite a big difference in torque in here. But again, I can control that with boost, and I don't really want a lot of torque. I have a transmission that's designed for this much torque. 600 newton meters is about 440. So it's like, this is what the transmission is designed for. Now, it'll take more than that, but I don't really want that. So this is the full, 103, 110, 117 on intake and exhaust. So this is the full sweeps. I mean, there's going to be other runs in here that are in between here, but this pretty much should bookend where I'm going to see the torque. You can see the torque comes up a little faster on this guy, but the power's down, and the torque comes up a little slower on this guy, but the torque's up. So very similar, just the spread is much closer, right? This doesn't have as big of a variation. And the horsepower, like even less. Like you wouldn't even, I mean, one's 1,000, one's 1,030, something like that. So, yeah. So this is average horsepower. This one here, you can see, has 20 horsepower more peak, 15 anyway. Oh, 1,043, yeah, 30 horsepower more peak. But this one has better average. So, and when you're looking at this simulation stuff, you can't like say, oh, it says it's going to make 1,011 horsepower. I put it on the dyno, didn't make 1,011. That's not how this works. Like it's called Performance Trends. Well, it's actually called Engine Analyzer Pro, but you're looking for trends. You're looking at, okay, where do I put the cam to get the maximum? Your flow bench is a steady 28 inches of water flow across it. And you can characterize your head by that and improve it, or prove that it's better or worse depending on what size valve and bulbs and stuff. But that doesn't mean that that's the only delta P across that valve that matters. So the simulations can only do so much with limited information. So really, if you wanted the simulation to be more accurate, you'd have to flow that cylinder head all the way up to, especially the exhaust, all the way up to sonic flow. And nobody does that because the dyno is the ultimate, the ultimate lie detector. So, but what we're looking for is trends. So we can see, okay, this is what it's going to be worth, and that, if it says it's plus or minus 10 horsepower, it's probably going to be close to that. The actual absolute numbers are probably going to be different, but you have to understand that when you're doing simulations. Like when you're doing finite element analysis, like the stress on that part may not be exactly what the stress on that part is, but if you made it better, it's better. And if you made it worse, it's worse. So that's what you really want to look at. And then testing to know that it's going to survive. So knowing that the difference between when you change the intake and the exhaust center line, it's in the 30 horsepower range delta. I wanted to kind of see what the difference was, just changing the intake center line and just changing the exhaust center line. So as you can see, the intake center line, you're kind of still seeing that 30 horsepower here, and the exhaust, you're kind of not. You're only seeing 15 maybe. So primarily the intake center line is what's given us a change. Like, it doesn't do diddly it down here, makes a boost come up a little bit faster, but these guys, yeah, that's not what's it's the intake that's given us this meat in here and this meat in here. So just know that. And then now, after simulating this and kind of suspecting, I wanted to see what kind of knobs I do have. So this is the intake runner length. So I think the normally aspirated one has 10 inches or so of runner after the bell mouth, from the ITB to the bell mouth in the plenum. So, and I think the manifold that I designed for the twin turbo is 8 inches or so. So I just wanted to see how big of a knob that is. And boy, it's a knob. Look at it's 1100 horsepower there, and it's 200 horsepower spread just by changing the rudder length from 12 inches to 2 inches. Now, yeah, that's a big number, but you'd have to have rocks in your head to run a long intake manifold. And maybe you don't want 2 inches, because I don't think that's really achievable, but I think I could probably achieve a 4-inch runner. And that's pretty nice. So, and this shows you why people do variable intake manifold runner lengths. What this doesn't show is if you tried to run a 2-inch long runner length on a passenger car that had a meat emissions and idle stability and stuff like that, it would suck down here because the fuel is jumping from one cylinder to the other and back and forth. So the longer runner helps because of the reversion in the intake tract. It keeps the idle stability better. I'm not worried about that, and my runner length isn't really 2 inches. It's 2 inches plus probably 3 inches for the individual throttle body, and then another 5.5 inches for the intake manifold or the port in the head. So I don't really have a 2-inch long runner, but that's the parameter that I varied it. So as you can see, this is a big knob. I'm going to optimize this knob when I build the new intake manifold. So this is essentially the difference between 6-inch runner to a 2-inch runner. So now some people would argue, oh, look at all this extra torque I'm going to have in here. That's awesome. I want to keep that. But that's not the way I want this thing to go, because I'm putting a kind of an arbitrary limit on 800 foot-pounds of torque, because I don't want to break transmissions and clutches and rear ends and stuff like that. So I'm going to be at an advantage by taking this up here, taking the power, and I can lose a little bit of torque here. And even if I need to fill this in with a little bit more boost, I can characterize my boost curve. So I can pick this up, and then I don't have to run more boost to get power up here. I can let the essentially free supercharging of the ram tuning effect give me that horsepower. So this is good information to have, and it's all combined inside your brain and into making those decisions. When you have control of everything, it makes it a lot easier. So the other piece of information that I thought I would check is out of the cylinder head. I believe I simulated the stock engine. I think it had a 1.5 intake or exhaust primary diameter. It's pretty small on the stock motor, and I'm going to build headers for this because got to have turbo headers anyway. So I think that was one of the differences between the stock S85 and the twin turbo. I went to 1 5/8 inch inside diameter, but as you can see, there's a lot more on the table here. If I go to bigger, now going to 2 inches probably we lose a lot in here and doesn't really gain much between 1.875 and 2, but going to 1 3/4 inches may make some sense, right? I'm not losing anything in here. So that's also a pretty big knob. That's 125 horsepower between the shittiest one. I mean, 1 3/8. Nobody's going to run that anyway. So, but still, this is 100 horsepower between that guy and that guy. So, all of this added together, I decided to run a new simulation with the short runner and 11 psi. So basically, this is what I had: 12 psi, and I shortened the runner to get more power, and then I lowered the boost. So now my boost is 11 psi. It's this curve here, this dark blue one, and the power is still 1,080 horsepower, something like that. Still a lot. So I could even turn the boost down more. And also what I could do is, if I wanted this thing to be 800 foot-pounds of torque, I could just bump the boost up here and leave it the same here. So I might have 12 pounds of boost here, 13 pounds of boost here, and then it goes back down to 11, and then it goes back up to 12. And then I have 800 from there all the way to there. And then this curve is just going to be straight. And what that does for me is that I don't put so much torque through the transmission, but I still have the average power. Because when you're shifting up here somewhere, depending on the gear, it's going to go, like in the lower gears, it's going to go back down to, probably in the 4,800 RPM range. So as long as I have full torque there, this isn't going to really help me, except for in first gear, which is probably going to be traction limited anyway. So, but second gear, third gear, fourth gear, these ones matter. And I can program, like if I'm traction limited in second gear, I know what gear I'm in. My computer can science that out, so I can have a different boost curve for each gear. So, and then if you take my final and compare it to normally aspirated, this is the normally aspirated curve, torque and horsepower here, red and cyan, and this is the twin turbo E85, curve. I haven't popped this back up here and this back up here yet, but I think I probably will do that once it gets on the dyno. So you have any questions, yeah, put something in the comments. But this program has been quite valuable to me. I used it when I had my own engine development, and we did actual engine development for OEMs, customers, ground cams in house, and dyno motors in house, and we did some big bore, big stroke motorcycle engines, and just all kinds of weird stuff. And yeah, it didn't give the exact number, but the trend every time we utilize this to improve something, the dyno said yes, that is correct. So I trust it to give me the right trend, but not give me the exact number. So anyway, like this content and want more, don't forget to subscribe, like, and share. And there likely will be a follow-up video on this, on actually how I'm mechanically going to deactivate the Vanos. I've had some. I disassembled the motor, so I kind of know what it all looks like. But there's going to be some machining and stuff. So probably some new pieces. And I want to make it adjustable because these cams will be, adjustable if I want to change something on the dyno and to change curves or whatever. So, and then I'll also weigh all the pieces before and after, because I have a feeling between the Vanos pump and all the hoses and actuators and stuff, I'm probably going to be taking 10 to 15 pounds off the front of the car. So that's going to help my weight and balance. I've been planning on doing a video on the weight and balance program, but I haven't done it. Doesn't seem like anybody is super interested in Excel crunching number videos, but it's super helpful if you're building a race car or a street car. You can make decisions before it's too late, right? If you put all the pieces in and then weigh it and go, oh, it's fucked up, it's too late, right? You need to know what those parts weigh, where they're going to live in the car, put it in your spreadsheet and go, oh, that's not going to work if I change to this steering rack, or if I move the motor this way or that way. Like, you have to know before, not just like put it on the scales at the end and go, crap, 70% on the front axle. That's not good. Don't do that. It's really hard on the front tires. I had a race car that did that. I mean, it's kind of a stock. Yeah. It wasn't really, it was a Lemons race car. It was a Saab 4-door Saab 9000, which when you take a big 4-door sedan and take all the weight you can out of it, it ends up all in the front because you need that stuff, and nothing in the back because you don't need that stuff. And then you have 70% of the weight on the front axle. And your poor front tires hate you forever.